So, hello everybody. Let us have a look at a LeetCode hard problem today titled binary tree cameras. So the question says, you're given the root of a binary tree and we install cameras on the tree nodes, and each camera can monitor itself, its parent and its immediate children. So we need to return the minimum number of cameras needed to monitor the entire tree, that is all nodes of the tree. For example, so if this was our binary tree, the minimum number of cameras that would cover the entire tree, that would monitor the entire tree, would be a camera just placed at this node, and that would monitor the entire tree. So this camera can monitor this node, its parent, and its immediate children. So in this case, the answer is 1. What about this tree, the one on the right? So in this case, the minimum number of cameras would be, here, if we were to place a camera at the root, we would probably need 3 cameras to monitor the entire node. But if we can place our cameras this way, in that case, we would need 1 camera here, and the next camera would be here. And this would monitor our entire tree. So parent, child, parent, and current node and child. So in this case, the answer is going to be 2. So the question asks us to return the minimum number of cameras needed to monitor all the nodes of a tree. So how do you go about solving this? What is the intuition? So in the first 2 trees, we are sort of covering the cameras in alternate levels. Is that the way to go about things? So let us try to ponder on that idea. If we were to place it at alternate levels, would it actually work in this case? So if we were to place a camera at the second node, and we would have to also place a camera at this node and at this node. So that would be 3. But we can actually simply do much better by placing a camera at the second node, as well as another camera at this node. And so with just 2 cameras, we are pretty much done monitoring the entire tree. This camera would monitor both of its children, and this camera would monitor its children as well. So, and this way the entire tree is monitored with just 2 cameras. So as you can see, the greedy solution is very tricky to implement, and you may need to cover a lot of corner cases. So let us not try to do that. Let us not try a greedy strategy. Let's just try out something that's much more intuitive to come up with, at least for me. So how would you go about doing this? Let us first try to construct a brute force solution to this. So if I were to just solve this problem recursively and try to come up with some kind of a recurrence relation, like how would I go about doing this? So clearly, every node, if I were to just go about it the brute force way, that would mean I have 2 choices. Either I can place a camera or not place a camera. And if you were to think about it, what does this fact of placing a camera also depend on? It can actually depend on the fact that whether or not the parent node has a camera. Because in some cases, if the parent does not have a camera, that means it is not covered. And who knows, even the parent of my parent may not have a camera. In that case, as a child, I need to actually ensure I have a camera so that my parent is monitored. So what I'm trying to say here is the fact that we are placing a camera may also depend on the fact that whether or not my parent has a camera as well. So if I were to just go about it the brute force way and try to write a recursive solution to this, so our magic function is going to calculate the minimum number of cameras that are needed to monitor the entire subtree that is rooted at a given node. And what all parameters are we going to give it? as we discussed, I'm going to give it the has camera parameter, whether I'll force the node to have a camera or not. The other parameter that can be useful is the fact that its parent node has a camera. So I'm going to give it two other parameters, that is has camera and if the parent has a camera or not. So both are going to be Boolean variables, and based on these two parameters, let me try constructing my function and work out the cases depending on what these values are. So let us have a look at the case when we are actually forcing the current node to have a camera. So I'm setting this parameter has camera to true. So how do we proceed in that case? Well, in that case, I'm interested to find the minimum number of cameras possible in the left subtree and minimum number of cameras in the right subtree, and I'll be adding 1 to that. So in this case, the answer is going to be 1 plus the minimum number of cameras possible in the left subtree plus the minimum number of cameras possible in the right subtree. And so what is the answer? Left cams and right cams. So how do we go about doing that? So well, we recurse. So I had 1 plus left cams and right cams. And how do I calculate the number of left cams? Well, I have two options here. My option 1 is that I can place a camera on the left child. So that would be f of node.left. I'm going to place the camera, and has parent camera is going to be set to true because I'm the current node and I'm actually like the parent of the left node, so I have a camera. So this parameter would be passed down to its children as well with the help of like has parent camera. So that is one case, and the other case is f of node.left. Well, I need not place a camera because it's covered either way, so I need not place a camera. And has parent camera is going to be set true, and I can do either of this, and I'm going to pick the one that gives me the minimum number. So that is going to be min of this or this. So that is yeah, how I calculate the number of left cameras, and the same would go with right cameras as well. So RC is going to be f of node dot right. I can either choose to place a camera or I need not place a camera. So but in all the 4 cases, has parent camera is set to true because the current node does have a camera. So this is why we have a choice, right? Like since the current node has a camera, that means like its children is monitored. But like, and now it's up to us, like it's up to us to decide whether placing a camera in the left or right child will like lead to an overall minimum number of cameras in the left and right subtrees. Like it's up to us to make that choice. So that is why we are evaluating all possible options. Like I said, this is brute force. It's considering every possible case, and out of that, whatever this magic function is returning to us, I'm going to pick the minimum mode out of this. So that is the case. That is case 1. When I said has camera to true, the answer is going to be 1 plus left cameras plus right cameras, and I calculate the number of left cameras like this and the number of right cameras like this. Now let us try to understand what would be the other case when the current node does not have a camera, and that is slightly complex, and let's try to go over that slowly. So let us now have a look at the second case when has camera is false, when the current node does not have a camera. So in the previous case, we'd seen we'd force the current node to have a camera. That is why we basically had to return 1 plus left cam plus right cam, because we are forcing the current node to have a camera. And so since the current node did have a camera, its children were at total liberty to decide whether or not to have cameras placed at them, depending on whether that would actually result in minimum in their respective subtrees. So it's something like this. If this was the current node, we are basically giving the children a choice whether to have cameras or not. And in this case, the child does need to have a camera so as to minimize the number of cameras in the left subtree. So that was just to give a quick recap of what we have been doing so far. So when has camera is set to false, so how would we go about doing things in that way? So here there's one small change, and that is we also need to take into account what the value of has parent camera is. And I'll try to explain the rationale behind doing that. So we are setting has camera to false, and depending on whether has parent camera is set to true or false, what our function is going to return is going to vary according to that. So let's have a look at the case when has parent camera is set to true. So let us call this case 2a. Then has parent camera is set to true. So if has parent camera is set to true, that means the parent node does have a camera, and the current node is monitored. So does this resemble anything? Like the current node is monitored, the parent node does have a camera. That's why the current node is monitored. So this again leads us back to the same recurrence we discussed in the previous slide, where we gave the liberty to the left and right subtrees to decide whether or not they want to have cameras. So it would be pretty much the exact same thing. So let me just copy paste this and paste it here. It will be pretty much the exact same thing, except for this, where we'll be setting it to false in this case, because our current node does not have a camera. So let me repeat. In this case, has camera is set to false, meaning the current node does not have a camera. And we are discussing case 2a, where has camera is set to false and has parent camera is set to true. So in that case, we give total liberty to the children to decide whether or not they want to have cameras. And we do pretty much what we did in the previous case. And here, I'm just going to pass on the parameter false, just to indicate that I do not have a camera. So in this case, I set it to true. And I just return. So what do I return? So I simply return LC plus RC, the number of left and right cameras. So this is what I return. So I just return this. In the previous case, I had to return 1 plus LC plus RC because I was adding a camera at the current node. Here, I'm not doing any such thing. So I simply, when f of current node has camera set to false and has parent camera set to true is called, I return simply LC plus RC. So that was case 2a. I hope this was clear. Let's now have a look at the case when has parent camera is set to false, when the parent node does not have a camera. So this is 2b. We are trying to calculate for the current node, when has parent camera is false. That is, the parent node does not have a camera. So case 2a was when parent camera did have a camera. And in both the cases, the current node does not have a camera. And we're trying to calculate what would be the minimum number of cameras for the subtree rooted at current node. So when the parent node does not have a camera, when that is set to false, how does that change things, you may ask? Well, I do want my current node to be monitored, right? So in that case, since my parent node is not monitoring me, that means either I'll have to force my left child to actually have a camera, or I need to force my right child to have a camera. And so either I need to force my left child or I need to force my right child to have a camera. Well, what does forcing mean here? Well, forcing simply means, so this is case 2b1, when I'm forcing my left child to have a camera. In that case, I'm going to be setting this to true. So it's going to be f of node.left, and I will force it to have a camera, and the current node does not have a camera, so the parent of the left child will not have a camera. Plus min of, it's going to be when I'm forcing my left child, the right child may or may not have a camera. Like, it's totally up to the right child. So the right child is at complete liberty. So in that case, like, I simply do f of node dot left, node dot right. So the right child can have a camera, or it need not have a camera. It's totally up to the right child. So 2b1, we are trying to force the left child, and similarly 2b2 would be when we are trying to force the right child to have a camera. So in 2b1, we actually force the left child to have a camera, and in 2b2, we are currently forcing the right child to have the camera. So in that case, it would pretty much be the same, except for some small change, that is, so in this case, we're forcing the right child to have a camera. So that would be so we are forcing the right child to have a camera, and the left child is at total liberty here. So the left child may have a camera, may not have a camera, depending on whatever gives it the minimum most possible number of cameras, and that would be case 2b2 when we are forcing the right child to have a camera. So, and why are we forcing either of them to have a camera? That is because we actually want to ensure that our current node is monitored, and by forcing either of the children to have a camera, we are ensuring that the current node is actually monitored. So, and our final answer is going to be the one that gives me the best possible result when I'm forcing my left child or my right child. So whatever gives me the best, I'm going to pick it. So that was simply it. So this is choice 1 and this is choice 2, and I just need to minimize whichever choice gives me the best possible result. And that was the case when the has parent camera is false. That is, the parent node does not have a camera, in which case I may need to force my left or right child to have a camera. So that is pretty much it. Just to recap, the first case was when we set has camera to true. In that case, we simply returned 1 plus LC plus RC, and both the left and right children were at complete liberty to pick depending on what gave them the minimum number of cameras. So the other case is when has camera is set to false, when the current node does not have a camera. So then we also need to consider like what the values of has parent camera was. So, and depending on whether it was set to true, we did this. We just returned LC plus RC. If has parent camera is set to false, in that case we needed to force the left or the right child to have a camera, and we arrived at this. So let's have a look at the coding section. Camera. So basically, how do we calculate the answer? Basically we have to calculate, we have to call the f function on the root node with the has camera set to true and has camera set to false, and whichever gives me the minimum number of cameras, I just use that as my answer. So that is going to be the minimum of the f function called for the root node with has camera set to true or false. So whichever is giving me the minimum number of cameras, that is going to be my final answer. And initially parent has camera set to false because the root node has no parent. And so this is the f function that we discussed. And let's have a look at the code. So this is the case one where we're forcing the current node to have a camera. In that case, it's going to be 1 plus left cams plus right cams, and where we give the left child and the right child of total liberty to decide what would give them the best possible odds to minimize the cameras. So, and then if the current node does not have a camera, in that case, it depends on whether the parent node has a camera or not. So if the parent node does have a camera, then in that case, it's very similar to this, except for the fact that we're going to return left cams plus right cams. Here we returned 1 plus left cams plus right cams. And here we passed on parent has camera as true because the current node has camera. Here it's going to be false because the current node does not have camera. So, and this is basically case 2A we discussed, and this is case 2B, where we basically force the left or the right child to have a camera, and we return the minimum of the two choices. And what is going to be the base case? The base case is when the node is none. So if the node is none and we have to have a camera, it just cannot be covered, right? So I just return infinity because we're trying to minimize, and since it cannot be covered, I just return infinity. Otherwise, I simply return 0. So because like if the none node does not need to have any camera, like this is going to be 0 cameras, right? So that is the base case. It's slightly tricky, but if you can just spend a couple of minutes, you should get this. So once the base case is handled, the rest we've discussed at length. So the only thing that's left is to realize that we are making a lot of unnecessary calls here. Like for example, we're calling min cameras on the left node with true and false set, and we're doing the same thing here as well, like here and here, and we're doing the same thing for the right node as well. And note that this can easily get exponential because we're making so many calls over and over again, and we're repeatedly doing that. So one way to speed that up would be to use memoization or top-down DP, and that is exactly what I'm going to do. So the key is going to be with 3 parameters: the node. You can also use the ID of the node. So the node and has camera and parent has camera. So this will be this like the DP with 3 states, and if it's already there, I just return DP of t. So this is going to prevent a lot of unnecessary calls, and it's going to speed things up. If it's not there, I store it in DP of key. I store my answer in DP of key, and I finally return DP of key. Return DP of key here, and let me just copy paste this and try running it here, and there you go. It's accepted, and that is about it. So we just had to prevent a lot of unnecessary calls, and hence we are actually using memoization to speed things up, and this was basically DP onto this. We basically solved it using brute force, and we just cached all the repeated calls to speed things up. And that is about it. Hope you liked the video and understood how you would go about solving DP on tree questions. And that is it for this video. Thank you for watching. Do subscribe, and I'll see you in the next one.